In today's video, we're going to look at section 6-4, polynomial functions. All right. Now, this can be a little tricky right away, but once we get into it, it becomes a little bit simpler. So please pay attention. So a polynomial in one variable. Now, that should give it away. There's only one variable. Okay. If there's more than one variable, it's obviously not a polynomial in one variable. It's a polynomial in two variables or three variables. So we got to keep that in mind. Now, a polynomial of degree n is one variable x is an expression of the form a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus and all the way up to a sub 2 x squared plus a sub 1 x plus a sub 0. Now, the coefficients a sub n minus 1 and so on just represent real numbers. It's all there. They're just coefficients, and they're just saying the next one down. Okay. A sub n is not non-zero, and n represents a non-negative number. So they're just the next the next coefficient in order. Okay. So for example, 3x to the fifth plus 2x to the fourth minus 5x cubed plus x squared plus 1. 3, 2, negative 5, 1, and 1. Those are the coefficients a sub n. That's all they are. Okay. So that's what we're talking about. All right. So now, here are some different polynomials. A constant is just a number, so it's 9. Degree of 0. The leading coefficient is 9. Linear, x minus 2 is degree 1 because it's x to the first. Quadratic, or squared. 3x squared plus 4x minus 5. The degree is 2. The cubic, 4x cubed minus 6. The degree is to the third. And then the general, what we just talked about in the last slide, a sub n x to the n, and so on, is degree n. Whatever it is, we just don't know it. Okay? So, state the degree and leading coefficient in each polynomial in one variable. If it is not a polynomial in one variable, explain why. So, if we look, now, the degree is the highest power and the leading coefficient is the number in front of the highest power. So, now, we got to make sure, one, there's one variable and that there's nothing screwy with it. So, everything looks good. There's only one variable. There's no negative exponents, and there's no square root x exponents. There's no variables in the denominator. So this is degree in one variable. It's a polynomial. So our degree would be our x to the fourth. Okay, so degree it's a fourth degree, and its leading coefficient, I'm going to put LC, is the number in front of that, which is 7. All right. So next one, 8x squared plus 3xy minus 2y squared. Well, right there, you see two variables, not one variable. There is an x and a y, so it's that easy to identify. Okay, so 7x squared minus 4x to the third plus 1 over x. Well, this we have an x in the denominator. We can't have that, so not a polynomial. X in denominator. Okay, next one. 1/2 x squared plus 2x cubed minus 5x, or x to the fifth, excuse me. So now there's only one variable, no negative exponents, no variables in the denominator, so we're all good. So our degree is the highest power, which would be 5. So degree is 5, and then our leading coefficient is the number always in front, which is right here. There's a hidden one, so it's actually -1. Okay, so it's that easy to identify. All right, so now the definition of a polynomial function. A polynomial function of degree n is a continuous function that can be described by an equation of the form p of x is equal to the general polynomial where the coefficients a sub n and so on represent real numbers. So we're looking for non-zero or real numbers. Okay, so we just got to make sure that we have all the rules we just talked about. So show the polynomial function f of r equals 3r squared minus 3r plus 1 gives the total number of excons when r equals 1, 2, and 3. Okay. All right, so r, number of rings. So all we gotta do is plug in. So f of r we'll start with f of 1 equals 3 times 1 squared minus 3 times 1 plus 1. So we get 1 squared is 1 times 3 is 3. So then 3 minus times 1 is also 3. So those cancel out. So we're left with 1. Next one, f of 2 is equal to 3 times 2 squared minus 3 times 2 plus 1. So again, 2 squared, 4 times 3 is 12. 3 times 2 is 6, so 12 minus 6 is 6, plus 1 equals 7. Okay, and the last one, f of 3 is equal to 3 times 3 squared minus 3 times 3 plus 1. So once again, so 3 squared is 9 times 3 is 27, minus 9, 18, plus 1 is 19. So now find the total number of hexagons in a honeycomb with 12 rings. Well, now we're just, again, plugging in 12. So f of r, so f of 12 is equal to 3 times 12 squared, minus, that's a minus sign there, 3 times 12 plus 1. Okay, so we've got to do a little work on this one. Can't do this in our, might not be able to do this in your head. So we get 12 squared is 144, 144 times 3 is 432. So I'm going to show my work on this one because bigger numbers. Minus 36 plus 1. So 432 minus 36 is 396. And then plus 1 would give us 397. So it would be 397 hexagons with given that there are 12 rings. All right. So it's kind of neat. So next one, find q of a plus 1 minus 2q of q of a if q of x is equal to x squared plus 3x plus 4. So this one, we got to plug in a plus 1 wherever there's an x. So we get, so I'm going to put this in, q of a plus 1 is equal, I forgot the second part, minus 2 times q of a. All right, so now, here we go. So anywhere there's an x, you put in a plus 1. So we get a plus 1 squared plus 3 times a plus 1 plus 4 minus 2 times a plus 1. Oh, no, not a plus 1. Now we're at just a squared plus 3a plus 4. All right, so the 2 is on the outside of this, so we got to distribute this 2 onto all of them. Here we have to, in the first part we have to FOIL, so we get a squared plus 2a plus 1. Then here we have to distribute also, so we get plus 3a plus 3. And we have plus 4. And then we have minus 2a squared minus 6a minus 8. So now I'm just going to combine like terms. So I got to grab my a squareds. So I get negative 2a, negative a squared because I'm subtracting, negative a squared, and then combining all my a's. So I got 2a plus 5a plus 3a equals 5a minus 6a, which is minus a. And then I got my regular numbers. So 1 plus 3 plus 4 is 8. And then minus 8, which is 0. So there we go. We're done. They all cancel out. So I'm left with negative a squared minus a. So here's some different graphs of polynomials. Constant is just a flat line. A linear function, degree 1, is just a line, a slanted line. Quadratic is a parabola. A cubic function has a little squiggly, and a quartic function is degree 4. A quintic function is degree 5. Okay, so now we're going to talk about how to identify what these look like. So bear with me, we are almost done. So here's some end behaviors of the polynomials. So we want to look at what the degree is. We're always focusing on the degrees. It's not changing color for me. I want to change it to red. Here we go. We want to always focus on degrees, whether it's even or odd. Okay, if it's even, the endpoints will be the same. Okay, and if it is odd, they'll go in opposite directions. Okay, and then we want to focus on the leading coefficients of that, positive or negative. Okay, so use this to reference, and if you follow these two things, it will lead you to these answers. If it is even and positive, this will be our answer. If it is odd and positive, this will be our answer, along with way down here. Okay, because they kind of move them. If it's even and negative, these are your answers. If it is odd and negative, these will be your answer. And I'll read off how to exactly say them. There's a lot to say here, so I'm kind of speed up. So using this chart will give you your answers every time, so long as you look at the degree and the leading coefficient. So here we go. Okay, so here we don't have it, but we can identify it. Describe the end behavior. So it is both pointed down, okay, for A. So that means, one, both pointing down, we can focus on the third step. It's even and it's negative. So our answers are going to be right here for A. As f of x goes to negative, f of x goes to negative as x goes to negative. So as we go, so our two answers are f of x goes to negative as x goes to negative, and also f of x goes to negative as x goes to positive. Okay, so if you follow that chart, this will be your answer. So now, same thing. It's both going the same direction, so that means it's even, but it's both going up, so that means it is positive. So, little glitch there. So here we go. F of x goes to positive as x goes to negative, and f of x goes to positive as x goes to negative or positive. Okay, so you can follow those charts every single time. So here we go. Now we got some ones going in different directions. Will we follow that chart? So as you look back, notice they're going opposite directions, and look for the graph that kind of mimics exactly what you got. So you got f of x goes, and it's going down as we go left, goes to negative as x goes to negative. Okay, and f of x goes to positive as x goes to positive. Okay, I'm literally just following the graph. I have the graph next to me. It's very easy to follow. I'm just looking for the similar shapes. So this one, I'm looking, f of x goes to positive as x goes to negative, and then f of x goes to negative as x goes to positive. So follow that chart, okay? You start to understand how these are working.